All right, hey guys, today we are going to learn about something called a geometric sequence, and we are going to be talking about recursive rules for geometric sequences as well. So while you watch this, you can either just take notes right in your notebook, or you can download these problems in Schoology. You will find them in today's folder. You're also going to want a calculator. All right, so before we get into today's lesson, I just wanted to go over the main problem that you did in yesterday's lesson and the answer key because kids were asking for it. So this is the first strand, this is the epsilon strand, and here's what you should have got if you graphed it. So you guys can't see this, but I did the table up here, okay? And then when I did the two regression, the line and the curve, so here was the first one, this would have been the line of best fit, this one would be the curve of best fit. You can kind of see by the equation, it looks like slope-intercept form, and this one looks exponential. Okay, so when you did that, clearly you guys can kind of see from the graph which one looks like a better model. I mean, look at the points here. It looks like the curve is following that much better than the line. I'll do that in blue. Then the line goes through the points. Now, here's how you can for sure tell. If you look at the R in both of them, which one is closer to 1? That's going to tell you which one is a better fit. Now, this one is definitely closer to 1, so I would say I would use an exponential regression. So to get your formula, then you should see your parameters down here. It gives you your A and your B. So I would say y equals, your starting value is, I'll just round that, about 17.9. Okay, and your B is about 4 to the x power. That is my rule that I would use. And it's pretty strong. That's got a pretty strong residual. So I would say that that is my formula for that one. Okay, and then on the omega strand, I'm going to apologize on this one. I got these two things from the high school, and I don't know. They have 7,000 in their table for 5, and we had 70,000. So I'm not even going to have you check this one. But the same thing, if you were graphing this one, I think both of them are supposed to be the exponential curve, but you always just want to look and see which one has the better R. That's how you can tell if a curve would be better or a line of best fit. You can also tell from the graph. I mean, the curve looks better here compared to the line. So no matter if you use 70,000 or 7,000, I'm not going to use the numbers because they use 7,000 in their table. So don't worry about that one. As long as you did the first one right, you are good. Now the last question that kind of popped up was question D on that page, and it said, do you think that these models will fit the data indefinitely? Basically, that means, will this model keep working forever for the data? Well, if this is a virus that is in your body, and the virus keeps, exponentially growing, eventually it's probably going to stop. So I would say it probably won't fit it forever. Indefinitely means forever, because eventually the virus is probably not going to keep, making more of it and making more and exponentially growing. So that's basically all that last question meant. Okay, so chapter 13 was actually only 2 lessons, and we just went through both of them. Make sure you check the homework that is in the back of your packet. I did just post it in the assignment from yesterday, so it's in yesterday's folder. You just might have to search for it, but please make sure you check that. I will take questions on the homework or on anything that you're not understanding when I come back on Thursday, but make sure you check that homework. So we're not going to test on this chapter yet because we are going to be doing chapter 13 and 14 together because it's like 2 lessons in each chapter and they kind of connect to each other. So today we're going to start the next little lesson. All right, so last chapter we worked a couple chapters ago, we worked with arithmetic sequences, and we talked about recursive formulas. So I want you to pause the video and I want you to just see what you remember about sequences, and can you answer all of those questions? All right, so we know this is an arithmetic sequence because there is a common difference of 3 each time. So it's going up by 3. Okay, so the common difference is 3. The first term in this sequence is 4. Okay, so it starts out with a 4 and then it's going up by 3. Arithmetic sequences have to be adding the same amount each time. So that could be adding like a 3 or it could be adding like a -4, but that's an arithmetic sequence. So we talked about recursive formulas. So recursive formulas, remember, help you find the next term if you know the one before it. So basically, if I know the term 16 and I want to, I can find the next term if I know the term right before it. So here's what the formula, recursive formula for arithmetic sequences look like. So they always listed the first term. This right here, again, means, hey, this is the first term. This is saying first term equals 4. And you guys can see that up there, it's 4. Now this part, if you guys remember from last time, this little part here means basically the value of the term before. So this is like the previous term. Okay, and we talked about this a ton when we were doing sequences. So basically, if you're trying to find some term number, I don't know which one it is, maybe I'm trying to find the 6th term, I would take the 5th term. Okay, so this is saying take the 6 minus 1, which is the 5th term, take the value of the 5th term, and add 3. Okay, so if I was going to do it, I would say 1, 2, 3, 4, 5. My 5th term is 16. That's the value of it. Plus 3 gives me 19. So this part right here basically just means the previous term, depending what term number you're trying to find. And again, if I want to find term 7, if I plugged in like a 7 here, then this would mean, okay, 7 minus 1 is 6. So I would find what does the 6th term equal and then add 3. So hopefully that's a good refresher. Okay, so if I have these sequences right here, some of them are arithmetic and some are not. If it's not arithmetic, can you still find some kind of pattern? And have we worked with this pattern before? So I want you to pause the video and try that. All right, so I just filled in each of the rules. So you can see that the arithmetic ones are letter A because the common difference is 2. It's adding 2 every time. Letter C, it's subtracting 5 or adding -5 each time. Those are the only 2 arithmetic ones. The other 3, maybe you noticed that the rule in this first one was multiplying by 2 every time. It was doubling. This one, it was dividing by 2 or taking half of it each time. And this one, I don't know if you guys saw this one, it's actually multiplying by -1. Okay, because a positive times a negative is a negative times a negative is a positive, and so forth. So it says, have we worked with this type of pattern before? Well, hopefully you're saying yes. When you are doubling something or having something, that is exponential growth. Okay, so hopefully you have seen this type of pattern before, and that will help us with these sequences. All right, so here I have a sequence, and these are actually called geometric sequences, which we'll talk about a little bit more in the next slide. But I have a sequence. I have 2, 10, 50, 250, 1250. So first it says, what is the first term? Well, it's clearly 2. Nobody should ever get that wrong, hopefully. So if I wanted to say that, I would say, okay, the value of the first term is 2. Okay, what is the common ratio? So it's not called common difference anymore. It's called common ratio in this one. Or what is the base multiplier? So you guys can probably quickly see this. It's multiplying by 5 each time. So that is 5. So now I just wrote a recursive formula for you. So basically it's saying, okay, if you know the term before, like if I know 1250, how would I get this next term? Okay, so all it's saying is, I'm going to tell you the first term, it's 2, okay? And then to find any previous term, or to find any term, like maybe I'm finding the 1, 2, 3, 4, 5, 6, maybe I'm finding the 6th term, which is right here. Okay, to find the 6th term, I would do, well, 6 minus 1 is 5. I would do the 5th term, whatever that is, times 5. And that makes sense. I would do 1250, because that's what the 5th term is, times 5. And that would give me the 6th term. So this is the recursive rule for a geometric sequence. Again, you may want to put this in your notes eventually, but this is, it's not always times 5, but it's times whatever the multiplier are or the bases. All right, so here is the actual recursive rule that you want to write for a geometric sequence. Here is what it looks like. They say to find any term, the value of any term, we have r times the term before. So they call that common ratio, or like the multiplier, basically. They call that r in this case. So basically, you're multiplying whatever the previous term was. So if I was writing notes on this, okay, I'd write geometric sequence. I would make a page that says that. Okay, and I would say this is the recursive rule. Okay, these are your notes, so you write whatever you want. And again, this is your multiplier down here. And this is the previous term, the value of the previous term. I'm even going to put value. Okay, so you might want to get that down real quick. All right, and then let's try one together that you might want to put in your notes. So I would go ahead and write this rule down. Okay, and I might just ask you for the recursive rule for this arithmetic sequence. So first thing I do is say, okay, it's pretty easy to see, it's doubling. Okay, so to write the recursive rule, you start by defining the first term. So the value of the first term is 3, right? I can see that here. Then to write the recursive rule. Okay, so to find any term number, okay, I take the multiplier, or the ratio, the common ratio, which we'll call 2, times f of n minus 1, the previous term. So again, all you're doing, so you always have to define the first term, and then to find any term, you multiply 2 times whatever the previous term is. Okay, so why don't you try letter A and letter C? All right, if you try letter A, it's multiplying by 4, so you guys should have had that to start with. So the first term, define that. The value of the first term is 2. To find any term number, you will take 4, that's the common ratio, times the previous term. There is your rule. All right, this next one, from 200 to 2,000, it's times 10. So you should have the first term is 200. Okay, and to find any term, you will take 10 times the previous term. Now, I should have had you guys try B. So if you guys can try B now, when you have one that is like dividing by 2, you're not going to write divide by 2. So you actually have to figure out what it's multiplying by. So on this one, it's timesing by a half each time, right? Dividing by 2 is timesing by a half. Okay, so now I can say, all right, my first term is 100. To find any term, I'm going to take a half, there's my common ratio, or my multiplier, times the previous term. So whatever my previous term is, I would just have it, times it by a half. All right, so sometimes the rules aren't quite as easy to find as the other ones that we were doing, like to get from 2 to 3 to 3 to 4.5. So if you're ever not sure, you just will take, just like we did with our exponential growth, you would take this number divided by 2. I would do 3 divided by 2, or 4.5 divided by 3, because I have to see, well, 2 times something is 3. Okay, well, I know 3 divided by 2 is 1.5, and then you can always just test it. See, does 3 times 1.5, does that equal 4.5? It does, and then 4.5. So there is my common ratio. So my recursive rule would be f of 1 equals 2. First term is 2. And then to find any term, I would take my common ratio, which is 1.5, times the term before, the previous term. You try letter B. All right, so letter B, again, you should take 87.5 divided by 350. Okay, if you do that, you get 0.25. Which makes sense. It's getting smaller each time, so it's got to be multiplying by a decimal. So my first term is 350, and then to find the next term, or to find any term, I'm going to take my multiplier, which is 0.25, or my common ratio, times the previous term. There is my recursive rule. All right, so I realize you may not have a lot of class time left because this is a shortened class. So you are going to try some of these problems here, this 14-1 homework. I posted in the Schoology. It is not going to be due until Friday. Okay, so if you don't get it done today, it's okay. Just start on it if you have time in class. If you don't have time, you will have some time tomorrow in class. But this is not due till Friday. So go ahead, try the ones that you think you can do. Only one I want to point out is number 7. I didn't do one like this, but it's got a graph of points. That's still saying like, okay, here's my first term is 2. So I would list, all right, my first term is 2. My second term is 6. My third term is 18. Now you should be able to kind of write a rule. So go ahead, try some of these if you have time. Again, not due until Friday because today is a little bit of short in class. If you didn't finish up the packet from the other day, you can also work on that if you still have some of that left. And we will work on this more in class tomorrow when I am back.